I hope you're enjoying the music, and good morning, everyone. Welcome to the IBM Qiskit Live Quantum Seminar Series, dedicated to you, the research and academic quantum communities. Now, in just a minute, I'll be thrilled to roll out this week's episode with Haoran Liao, reporting on work done here at IBM Quantum with yours truly, and finishing his PhD at UC Berkeley. But before we get there, I'm so glad you've joined us on time. We have this tradition to give everyone just a minute or two to tune into the live stream and to get active in the chat. So you guys already know my favorite question, which is, where is everybody tuning in from? Where are you dialing in or watching on YouTube? You can reply to that in the comment chat box on YouTube, located somewhere on your screen, left, right, above, or below, which is the same place that you can also ask questions live of Haoran and any of our speakers during the presentation. And I'll bring those up so that we can have a lively and interactive discussion. We like to keep this the chat going and flowing in here. And I think with that, folks, let's get to announcements. And I have two very special ones. One, the Qiskit Summer School videos are online. It's a 2-week intensive summer school. We had amazing lectures on all kinds of topics from John Watrous, Olivia Lanes, myself, and many others, Nick Braun, walking you from theory to practice and giving you all the basics you need to know to get into the field, to reaffirm and reskill your knowledge, and to understand and also do your own independent research on topics like the one you hear about today. And with that, I'm excited to also say that we have some very special series coming up, such as a quantum paper review series that will be coming up shortly, and lots of good stuff down the pipeline. So with that, folks, don't forget to click like and subscribe, and we appreciate that very much. And let's get to episode 140. I'm your host, Zlatko Minev from IBM Quantum Research, and I have the pleasure and delight to introduce you to Haoran Liao, reporting on work done at IBM Quantum and finishing his PhD at UC Berkeley. Hello, Haoran. How are you today?
Good, thank you. I feel good. How are you?
Great. I am really excited for your talk. I've been going to a few conferences, and your paper just came out on Monday, and people have already been bugging me about it and telling me, oh, this is really cool and exciting. So really looking forward to it. I should tell you, because there's a little bit of delay in the chat, that today we have folks from San Diego, Stockholm, Spain, Ecuador, India, Greece, Italy, Pakistan, New York, Pittsburgh, Atlanta, Zurich, Chicago. So thank you everyone for making it here for this seminar across all the time zones. Now, allow me, Haoran, to introduce you briefly before I turn over the stage. Haoran is a senior PhD candidate in physics at the University of California, Berkeley, my own alma mater, where he is advised by Brigitte Whaley, none other than her. Haoran received his bachelor in math and physics from McGill University, and he's recently completed an internship at IBM Quantum under the supervision of, well, yours truly, and also the amazing team here on the paper you will see. As a bit of a dream team, and it's resulted in this paper you're about to hear. So Haoran, with that, the stage is yours.
Thank you, Zlatko, and thank you everyone for the opportunity to speak here at the Qiskit seminar. So I want to talk about our work on machine learning for practical quantum error mitigation today. The work has been posted on arXiv, so welcome to check it out. And I hope that this seminar and our work can bring some new perspectives on using machine learning to enhance quantum computations and also motivate more discussions on that. So Derek, Iskandar, Elraza, Zlatko, Ciro, and I contributed to this project with the help of many amazing people at IBM Quantum. So I want to thank everyone for making this happen. And quantum error mitigation essentially trades additional execution time for increased accuracy in the targeted expectation values. It provides a path towards fault tolerance, towards useful quantum computation before the introduction of fault tolerance. And if we chart the runtime, quantum runtime, as a function of circuit complexity on classical computer, quantum computer with error mitigation, quantum computer with error correction, we see that quantum error mitigation fills the gap before error correction achieves practical runtime reduction. And one extensively studied quantum error mitigation approach is the probabilistic error cancellation, where the noise in the circuit is learned layer by layer and then probabilistically canceled on average over many, many mitigation circuits. So welcome to check out this blog for more detailed introduction on PEC. So in principle, we get unbiased expectation values from PEC, but the cost is an exponential overhead to achieve the desired additive accuracy in the targeted expectation value. So it is rather expensive. To give some perspective on that, for an error rate that's as low as on the order of 10 to the negative 4, it takes about a day to mitigate a circuit with 100 qubit and 400 depth. On the other hand, a popular alternative is zero noise extrapolation, where the zero noise expectation value is obtained from extrapolating from those obtained at various noise level. And in practice, we usually use 3 noise level, so that means 2 additional mitigation circuits. It is relatively cheap to implement, but the downside is that we get biased expectation values. Our machine learning approach, on the other hand, doesn't require any additional mitigation circuit at runtime, so it has arguably the lowest runtime overhead. But of course, there's no free lunch. We're essentially putting the overhead in the training of the model. So the machine learning approach offers significant advantages in runtime efficiency by front-loading training for on-the-fly error mitigation. And we want to stress here that the machine learning part here is not to learn the device noise, as in quasi-probability-based error mitigation approaches like PEC or PEA. So our work aims to investigate the practical utility of this kind of machine learning approaches in the context of error mitigation. We ask the question of how well it performs under realistic noise, how efficient it can be even if we consider training overhead, in what use cases can it be particularly useful, and whether or not it can scale to classically intractable circuits. So in the remaining of this seminar, I will provide evidence suggesting positive results in all these aspects. So before going into the details of the results, I will briefly go over the workflow of our simple machine learning for quantum error mitigation. So the first step is to generate training data. We generate a large number of training circuits that look similar in structure to the circuit of interest. We pass those circuits into the encoder to get the circuit level features, such as the gate counts. And we also pass them through the QPU to get the noisy expectation values. If these training circuits are small scale, they can be passed into the noiseless simulator to get the ideal expectation values. And we set that as the target expectation value. Otherwise, we can get the expectation value mitigated by another error mitigation method and set that as the target. The second step is to train the machine learning model to regress the circuit level features and the noisy expectation values onto the target. If the machine learning model requires iterative update, then the output at every iteration is fed into the loss function together with the target expectation value, and the optimizer would try to minimize the loss function in that iteration by update the model's parameter. And the training is considered complete when the loss function converges to some minimum. After training at runtime, all we need to do is to pass the circuit of interest into the encoder again to get the circuit level features, and through the QPU to get the noisy expectation values, and then we can feed all of them into the trained machine learning model to get the mitigated expectation value. So we stress that there's no additional mitigation circuits needed at runtime, and that's how we achieve our runtime efficiency. So welcome to leave any questions in the comments and I'm happy to answer them during my presentation. So to those of you who are familiar with quantum error mitigation, you may wonder what's the difference between our approach and a previous machine learning approach called Clifford data regression. So there are three major differences. The first difference is that CDR collects largely Cliffordized circuits for training, and we don't have that constraint. What we're asking is that there's some similarity between the training circuits and the testing circuits. And CDR doesn't work on circuit level features, so it doesn't have this encoder component. And also, CDR uses only linear regression as the machine learning model for mitigation. And we can comment a bit more on that. So when the noise channels in the circuit are successive depolarizing channels, one can show that there is an exact linear relationship between the noisy expectation values and the ideal ones. But when the noise model becomes complicated, not to mention the realistic noise, it really prohibits from getting the exact relationship between the noisy and the ideal expectation values. A spherical count metaphor that people usually make in physics. So that motivates us to think about nonlinear models. And we expect that nonlinear models will, in general, model this relationship better and produce better mitigation results. So to that end, we survey a broad spectrum of machine learning models from simple to complex, starting with the linear model, linear regression, and going into nonlinear models like random forest regression, multi-layer perceptron, and model as complicated as graph neural network. So the input to the linear regression model is a vector consisting of noisy expectation values, circuit level features like gate counts, and also encoded observables. And we use the sparse poly encoding, and there will be ones or zeros in those entries. And they essentially serve as indicator variables to the linear regression. The same input will also be fed into the random forest. And random forest is an ensemble learning method that consists of a large number of decision trees. So every tree in the forest works on a bootstrap subset of the input training samples, and as well as some features. For example, the first level splitting in tree 1 is based on the noisy expectation values. If it's greater than 0.5, we go to the right node in the next level of splitting. Otherwise, we go to the left. And associated with every leaf node in the decision tree is the output of that tree. And the random forest will average over all the predictions from different tree and call that the mitigated expectation value. For a multi-layer perceptron, which is the simplest neural network model that we can think of, we again feed into the MLP the same vector. And MLP can be thought of as successive layers of linear regressions followed by nonlinear activation functions. And then it's the most complicated model that we ever consider, which is GNN. So it is good at extracting interdependent relationships among nodes in a graph. And it's also good at extracting global informations of a graph as a whole. Quantum circuits can be naturally represented as an acyclic graph, where the node represents some operations or gates, and the edges in the graph represent the qubits. So for example, this node in the graph represents a Hadamard gate, and this edge represents a qubit on which the Hadamard gate ends. And we further encode into this graph some vectors. And those vectors will indicate, for example, on this node, the gate type and also the gate error. And the vector assigned to this edge will indicate the coherent times of the qubit. This graph structure and the encoded vector will get passed into the message passing layer, where some nonlinear function will aggregate information and update those vectors based on the vectors assigned to neighboring nodes and neighboring edges. All of this will get flattened and passed into the multilayer perceptron along with the noisy expectation values and the encoded observable to get the mitigated expectation value. So I'll pause here a little bit in case there's any question. Again, welcome to leave any comments in the chat.
Yeah, and thank you folks for posting these questions. So there are a few here, and maybe we'll get to some of these in a little bit. Let's start with just the question around the similarities of the training circuits and the circuits of interest. I'm not sure you've gotten there yet and have talked about that. So you feel free to punt that one to a little bit if you have a slide on it.
Yep. So I think that's this step, where we generally ask that the training circuit to be similar in structure to the circuit of interest. But again, there may be exceptions, and we don't really have like a very general rule of generating training circuits. We tried on trotterized circuits, we trained on trotterized circuits, and also test on trotterized circuits. But we also tried, training on random circuits, and it also works with random circuits. So yeah, there's no like a definitive rule on how to choose training circuits for this kind of model.
Yeah, and maybe the examples you show us will make this even more clear in a few slides.
Right.
Great. And then a question from, thank you, Monica, and a question from Kevin. What is the largest machine learning model and parameter set that has been used? In other words, how large and complicated are these machine learning models?
Yeah, so the most complicated model in terms of parameter count is the GNN, and the largest one we've tried have on the order of 10,000 parameters. Maybe 30,000 parameters, the largest one we've ever tried. Actually, maybe 100,000 parameters, the largest one we've ever tried. The thing is, it will probably become clear later on in my talk that graph neural network and also complicated models tend to overfit. So it's not that the more parameters we have, the better performance they have. On the other hand, simple models like random forest, where we only use like 100 trees or up to 300 trees in this forest, perform pretty well.
Great. Another question just came in. Let's see. Okay, yeah, maybe can you clarify a question from Ron? When talking about the encoding vectors, can you clarify a little bit more what the encoding vector means?
Yeah, sure. So the encoding vector essentially gives us the features for the regression. And those features are circuit level features, meaning, for example, gate counts, gate depth. On the other hand, we also have features that's not technically on the circuit level feature, on circuit level, and for example, there are expectation values. And I'm showing an example here of the encoding vector. It has an entry dedicated to the expectation value. There could be multiple of them if we are measuring multiple expectation values that are commuting. And we also have entries that encode gate counts. For example, here N2Q means the 2-qubit gate count, and NSX means the gate count of SX gate. If the gate is some parameterized gate, we will bin those angles and count by those bins. Does that answer the question?
Yes, thank you, Haoran. And folks, thanks for all the questions. I think some of these that I'm seeing, which model is the best and so on, that's the rest of the talk. So hang tight. All right,
Yep.
Here I am. Thank you.
So here are the key results of our work. So using a general framework for machine learning or quantum error mitigation approach, we invent and survey a broad spectrum of simple to complex machine learning models. And we find that random forest performs the best. On small scale circuits, we show that the machine learning approach significantly and consistently outperforms digital Z&E with lower overhead in both simulations and actual experiments. On large-scale circuits, we demonstrate in Haoran experiment that the machine learning approach can significantly improve efficiency of existing quantum error mitigation methods. So in the remaining of this seminar, I will go through a series of noisy simulations and Haoran experiments to support those results. So we'll start with noisy simulations because it allows us to conveniently tune knobs, for example, varying the noise models. We'll look at two examples, the random forest, structured circuits, and in the structured circuit simulation, we'll vary the noise model to try to understand what the machine learning model can do and cannot do, to try to gain more insight into this black box. And later, we will go through two use cases that we think the machine learning approach can be particularly useful. And lastly, we will show Haoran experiment suggesting that the machine learning approach can be scaled to a classically intractable circuit. So let's look at random circuits. We train the machine learning model on 5,000 and test on 2,000 random circuits with 2 qubit gate depth up to 18. This is noisy simulation, and the noise model considering here consists of incoherent noise and spam error. So shown on the left is the error distribution of all the machine learning model as well as DNA. The error is computed from either the unmitigated expectation values or the mitigated ones to the ideal ones. And we see that all of the machine learning models produce these results that have error closer to 0. We also observe here that there are some outliers in the noisy expectation values as well as in the expectation values mitigated by the machine learning model. So as you see more evidence later on, that one explanation is that the machine learning model is trying to give a prediction largely based on the noisy expectation value. So, and it's in a way that doesn't change the noisy expectation value too much. So if the noise expectation values is an outlier, the machine learning prediction likely remain as an outlier in this mitigated distribution. Shown on the right is the bootstrapped mean of all those error distribution with an error bar showing 95% bootstrapped confidence interval. We see that all machine learning model outperforms DNE, and notably random forest outperforms all other machine learning models. And as we will see more evidence later, or in the paper that we talked more about this, we show that random forests consistently outperform other machine learning models. So I will pause here a little bit actually, in case there's any question.
Yeah, thank you. And folks, feel free to post questions as we go in the chat, and Physics in Our Universe might begin to answer your question, but I think there's more to the story here. And I think for now, Haoran, maybe just summarize the main messages at this stage for these random circuits, which can look like anything. Random forest seems to do the best, but we have to see more on it, on the performance. So folks, unless more questions, let's carry on.
Sounds good. Yeah. So at least in this particular task on random circuit, which lies on one extreme of the spectrum in terms of circuit structure, we see that the machine learning model seems to generalize to structures that doesn't need to be similar. And the second task that we looked at is on the other extreme of the spectrum in terms of circuit structure. And we focus on the 1D transverse field Ising model, the first order tritorization. There are two parameters here, the J, the coupling strength, and H, the transverse field strength. So we train the machine learning model on circuits with up to 14 trotostep and test on circuits with up to 28 trotter steps. So one trotter steps amounts to a circuit that looks like this with 4 layers of CNOTs. And the RZCX is a canonical decomposition of the RZC interaction. And in this simulation, we will vary the noise model and see what the machine learning model can do and cannot do. The first noise model that we looked at consists of only incoherent noise. So shown on top is the error from either the unmitigated or the mitigated expectation values to the ideal ones as a function of trotter steps. The dashed line here separates the trotter steps that were included in training in what we call the interpolation regime from the trotter steps that were not included in training in the extrapolation regime. So I emphasize here that all of the data point here, whether it's in interpolation or extrapolation, are all testing data points, meaning that all of those J/H ratio are different in the testing set and the training set. And we see here that the machine learning produces results that's much better than ZNE across all trotter steps. And shown below is the time evolution dynamic of a single trajectory, meaning a single J/H ratio. And here we see that the machine learning results, which is shown in the red curve here, pretty much overlays the green curve, which shows the ideal time evolution. And next, we add some readout error to the noise model. And that degrades the performance of ZNE, digital ZNE. And that is expected because ZNE naively will not be able to mitigate error that doesn't scale with folding the gates. And we again see that the machine learning approach significantly outperforms ZNE across all trotter steps. And then we add additional coherent error into the noise model. The coherent error here is CX over rotation. We see that in the interpolation regime, wherein we have circuits with number of trotter steps that were already included in training, we see that our machine learning approach, again, significantly outperforms ZNE. And ZNE pretty much failed after trotter step 7. That is kind of expected because coherent error is pretty strong in the sense that it affects the expectation value in a quadratic way, whereas incoherent error only induces linear change in the expectation value. So coherent error is pretty detrimental in that sense. Interestingly, in the extrapolation regime, none of the error mitigation works. And perhaps we can know more information in the single trajectory shown below. The green curve shows the ideal expectation value over trotter steps. And we see that the red curve, which is the machine learning results, gives a curve that has an oscillation frequency that's increasingly out of sync with the ideal ones. And also the noisy expectation values, which is shown in the blue curve, is also increasingly out of sync with the noisy ones and is pretty much sharing the same frequency as the machine learning results. So that hints at the fact that the machine learning model is trying to make a mitigation largely based on the noisy expectation value, and is, it will not be able to change the oscillation frequency significantly that it match with the ideal expectation value. So I want to stress here that our machine learning approach works in the extrapolation regime, meaning that it can generalize to circuits deeper than those included in training. We also study the trotterized circuits on actual hardware, and we are not employing any additional error suppression or error mitigation technique. So there is coherent error in the experiment. We're looking at the interpolation regime where all the trotter steps were included in training up to trotter step 9. We see here again that the random forest, the machine learning approach, outperforms ZNE significantly. And in fact, in this experiment, we have advantages not just in accuracy, runtime efficiency, but also in overall efficiency, including training. So with 2,500 testing circuit, ZNE with 2 noise factor will require 5,000 executions. For the machine learning approach, it requires 2,500 execution at runtime. And to produce this result, we train the model with only 500 circuits, so that incur 500 circuit training overhead. So the total overhead of the machine learning approach is 3,000 circuits, which is 40% lower compared to ZNE. So we have here also higher overall efficiency. So in practice, the noise in device will often drift over time, and that can frequently incur training overhead. So we are unsure whether the machine learning model can generalize to drifting noise. That remains an open question. But at least, even if it doesn't generalize to drifting noise, we show that they can still be efficiently adapted to a new noise model, or the drifting noise. For neural network models like MLP, they can be fine-tuned, meaning additionally trained on a small number of samples collected from the drifted noise. And for random forest, we can't really fine-tune it. It's a simple machine learning model, but it is already very efficient in training. And we can just train it from scratch using the sample collected with the drifted noise model. And all of this is shown in the plot here. We're plotting the testing error on the drifting model as a function of additional samples collected from the drifting model. And we see that both MLP and random forest perform very well after training on just a small number of additionally collected samples. So I will pause here in case there's any question. Okay.
I think, folks, this is a good time to post more questions, but right now I think you can keep on.
Sounds good, thanks. So now let's look at one use case that we find the machine learning approach can be particularly useful, and that is to mitigate unseen polyobservables. So we trained the machine learning model on a subset of all the polyobservable and asked it to mitigate the expectation values on all the remaining polyobservables. Shown on the right is the error on the remaining polyobservables as a function of polyobservables that were trained on. And we see that there is a quick crossover between the random forest and ZNE, meaning that we only need to train the random forest with a small fraction of polyobservables, and it can outperform ZNE. So this can be particularly useful in cases where we need to mitigate multiple polyobservables for the same circuit. And we just need to train the random forest or the machine learning approach with circuits measured in a selected subset of those polyobservable, and it can generalize to mitigate the expectation values of all the circuits. And the second use case that we find the machine learning approach can be particularly useful is to enhance variational algorithm. So in the typical workflow of, for example, VQE, the noisy estimate, the energy estimate coming from the variational ansatz on the QPU will get passed into the optimizer, and the optimizer will try to update the parameters in the ansatz to give a new estimate in the energy that's supposed to be lower. So we add into this workflow an error mitigation step. The noisy energy estimate is first error mitigated before passing into the optimizer. And the error mitigation is either done by ZNE or the machine learning approach. And we use this modified workflow to map out the dissociation curve of the hydrogen molecule. And here we see that the red curve, which is the machine learning mitigated expectation value of the energy estimate, the final energy estimate, is pretty much the same as the ideal ones at all bond lengths. And it significantly outperforms ZNE across all bond lengths. And we see that the error for the machine learning approach is almost 1 order of magnitude smaller than the error coming from ZNE. And what's more, we are actually also using the fact that the machine learning model can generalize to unseen polyobservables here. So the Hamiltonian of the hydrogen molecule consists of XX, Zi, Iz, and Zz terms. We are only training the machine learning model with circuits measured in XX and ZZ. So in order to get the energy estimate, the machine learning model needs to generalize to the circuit measured in Zi and Iz here. And lastly, I want to argue that our machine learning approach can scale to a classically intractable circuit. So that is done by instead regressing onto expectation values mitigated by another error mitigation method. So we are replacing the noiseless simulator by the error mitigated QPU here, and use that as the target expectation value that our machine learning model will regress on. So in effect, the machine learning approach reduces the runtime of traditional quantum error mitigation methods. And we demonstrate this with a 100 qubit experiment with, again, the 1D transverse field Ising model with up to 10 trotter steps. And one trotter steps has 4 CNOT depth, so up to 10 trotter steps, we have up to 40 CNOT depth, and that is very close to 2000 CNOT counts. So before going into this mimicry of another error mitigation method, we need to first show that the error mitigation we are mimicking produce meaningful results on this 100 qubit circuit on the hardware. And we are doing this on the Clifford parameters of the 1D transverse field Ising model so that we can easily get the ideal expectation values. And the error mitigation method that we're mimicking is, again, digital ZNE, which is shown as the orange curve here. And we see that it achieves significant improvement over the unmitigated results and is much closer to the ideal ones. So it's meaningful for us to mitigate it, to mimic this ZNE. And I want to mention that because it's 100 qubit large-scale experiment, the coherent noise could be very detrimental, and we are performing polytwirling here to suppress the coherent error. So all of the results that I'm showing here and will be shown later are twirled results. So establishing the fact that we are mimicking something that's meaningful, we now train the machine learning model to mimic the results coming from digital ZNE on the non-Clifford circuits. So shown here are 2 example traces, meaning 2 H over J ratio. And we see that the machine learning result, which is shown in the red curve here, aligns very well with the orange curve, which is the ZNE result. And the error here is computed over all the testing circuits, meaning over 40 different J over H ratio. It gives an empirical error bound on the mimicry. And we argue that the error can be pushed much lower given more training data. And we are really limited by the number of training data here that we're only training on 100 circuit because we are also additionally doing twirling. So the actual number of execution is much higher. In fact, we also achieved not just runtime efficiency, but overall efficiency in this experiment. So for ZNE with 2 noise factor, testing on 400 circuits requires 800 execution. For the machine learning approach, at runtime, it requires 400 execution. And to give this result, we are only training on 100 circuits. And because we're mimicking ZNE, so there should be 200 execution for the 100 training circuit. So for the machine learning approach, the overall overhead is 600, and that is 25% lower compared to ZNE. So here is a summary.
Before you get to conclusions, maybe a few questions on from folks here. So maybe I'll start with Jeffrey's question. Jeffrey Cohn, thank you for this question. Can this be used in conjunction with dynamical decoupling and polytwirling?
Yeah, so definitely. So polytwirling and dynamical decoupling can help with the coherent error. And we've shown before that the machine learning approach kind of fail with coherent error, especially with deeper circuit. So if we also employ dynamical decoupling and polytwirling to take out the coherent error, then maybe the machine learning model can generalize to actually deeper circuit.
Excellent, thank you. Let's maybe take one from Kyle. It's impressive that the random forest model outperforms the neural networks to this degree! Exclamation mark. This may be related to the fact that the 4 qubits system is very small in the earlier data you showed, and this is now 100 qubits, but the earlier data was started with 4, and you kind of built your way up to 100 in the training set. Maybe neural networks are more competitive at larger system sizes of training. Can you tell us more about that?
Sure. So that's a good question. So definitely it's possible. It all boils down to, how complicated those relationship is between the noisy and the ideal expectation value, and whether a complicated model can overfit here. So our intuition on why machine learning neural network approach underperforms simple models like random forest is that the effect of noise on the expectation value is not really that complicated to learn. So, more advanced methods like neural network approach actually overfit here. But it's definitely plausible that with larger circuits, neural network may outperform random forest.
Excellent, thank you. And a question, well, maybe Sonam's question will come to in a minute. How about that? Because I want to get on this. Before we move to your conclusions, a question on, can we do mimicry on Clifford circuits with the same J over H? Maybe that's a clarification question.
So mimicking Clifford circuits with the same J over H, does that mean we train on non-Clifford circuits? Oh, sorry. Mimicking I see. So yeah, it should also work. We are only picking out the Clifford parameter here because we can, extract the ideal expectation values easily and use it to do verification. But there's nothing preventing us to put the Clifford circuit into our testing set and also training set.
Awesome, thank you. Yeah, and feel free to clarify the question, but maybe it's, as you mentioned, here you did this Clifford version at J0. It's a Clifford circuit. It's classically simulable. So we know what the answer is and we can check against it. But for the other ones, we don't know what the answer is because it's kind of hard to simulate. Maybe somebody could figure that out, but we didn't. So that's those are non-Clifford. And there are a few more questions, but let's leave those for after your conclusion.
Sounds good. So here is a summary of what we found. So using a general framework for machine learning for quantum error mitigation, we enhance and survey a broad spectrum of models, and we find that the random forest performs the best. In noisy classical simulations, we find that the machine learning approach significantly and consistently outperforms the traditional method, digital ZNE, in a variety of tasks under various noise models with different circuit structures, and even testing on circuits that are deeper than those included in training. It also works well in mitigating unseen polyobservables and can be used to enhance variation algorithms like PQE. And in actual hardware experiment, we show that the machine learning approach significantly improves both accuracy and efficiency of a traditional method on small-scale circuits, and it improves efficiency on large-scale circuits. So we no longer have the advantage in accuracy for the large-scale circuit because we are doing the mimicry, but we still have runtime efficiency, and in the experiment, we even show overall efficiency. So there can perhaps be some future directions along the line of using machine learning for quantum error mitigation or even error characterization. So it's an open question whether we can train GNN on a large amount of data with different noise level, and the GNN can figure out how to extrapolate to expectation values that's quite close to the ideal ones. If that is the case, then it frees us from requiring ideal expectation values and make the method scalable, and also allows the potential advantage in not just runtime efficiency, but also accuracy over other methods. And perhaps we can also invert the way we do the regression. Instead of regressing the circuit level features and the noisy expectation value onto the ideal, maybe we can regress the ideal and the noisy onto the noise parameters. And of course, for our work, there can be some optimization in the training set, further optimization in the training set, and also the type of training circuits that were used. Perhaps we can put more emphasis on deeper circuit, so that reduces the training overhead because deeper circuit could bear more information. And also we can benchmark our machine learning approach against leading methods like PEC, PEA, and analog ZNE. So instead of folding the gates, we're stretching the pulses there. So that would give us a better sense of how this machine learning approach perform compared with the state-of-the-art method. So I'm happy to take questions. I will leave this slide on the conclusion so that people can look at it. And also welcome to check out our paper on arXiv, which is listed here.
Thank you, Haoran. Great presentation. Congratulations on the great results from just a relatively brief internship. I hope you enjoyed it. And we do have a lot of questions. So folks, feel free to post more questions. We actually have probably a tremendous amount of time here compared to where we usually end up. So great job on the presentation as well. Let's start with Sonam's question. Can random forests outperform probabilistic error cancellation?
Yeah, so on small scale circuit, possibly. On large scale circuit, currently we can only do mimicry, meaning that if we if we're mimicking ZNE, perhaps we wouldn't have a chance to outperform PEC, because I think PEC in general performs better than ZNE. And if we're mimicking PEC results, assuming that we can actually mimic, because scaling PEC to large scale circuit is difficult, then we could not really claim that we outperform PEC, because we are really just mimicking it. We can outperform PEC in terms of efficiency, but not accuracy.
Yeah, and maybe I can, as one of the authors of PEC and this one, maybe I can add some flavor here as well, if that's okay with you, Haoran.
No, not sure.
Yeah, I think Haoran nicely points out that there are two axes here, right? There's accuracy. Where's the camera? And then there's runtime. So, accuracy and runtime. I think on accuracy, that's where PC will generally give you the unbiased estimators, provably so, up to some learning error. The challenge is with the runtime. The runtime is huge. And I think what these machine learning algorithms are showing us is that we can tremendously reduce that. So probably it can outperform there significantly, especially at scale, as Haoran mentioned. And it seems like this mimicking also allows you to mimic the output of PC, but perhaps PEA, it's basically PC and Xeni combined, can also be another way to combine those two results at scale, because it's trickier to do PC at scale of 100 qubit experiment like we did here. So I think in that sense, probably the answer is yes, it can outperform because of the runtime efficiency. And in principle, PC can always outperform in terms of accuracy, but in reality, the runtime becomes a major question. So kind of have to work with both of these axes at the same time. So thank you for that great question. Maybe the next question we'll take here is on, let's do this one first from Kevin. There are classical models with trillions of parameters that can be run. Quantum errors are prevalent and abundant. So, would it help to have larger models? Can that improve things?
Yeah, so that's an open question. We're not sure whether the large model can help. Perhaps it can, especially with large-scale circuits with huge amount of data, um, um, and hopefully that even with much deeper circuit, the noise is complicated. But I think there have been studies suggesting that in deep circuits, the noise tend to become depolarizing noise, and that the noise structure is relatively simple. So perhaps even in the large scale deep circuits, simple machine learning models will still perform quite well.
Excellent, thank you. And thank you, Kevin, for the many questions. Let's go back up to a question. Oh, also by Kevin. Wait, yes, also by Kevin. Can you provide more details on the random forest model used, and maybe just kind of walk us through one of these trees? How does that tree work? Is it a binary? What are the outputs? Is it a 0 or 1? Is it a continuous number? Maybe just help walk us through that a little more carefully with some example.
Yeah, it is not a continuous number. So in the training, eventually one sample will go down the tree in different splitting and end up at nodes. And
when you say one sample, is it an expectation value, or maybe clarify for us what you mean by that?
Yeah, so one sample, it consists of circuit level features and also the noisy expectation values. Those splitting will be based on those features. Associated with every node, the tree will assign a number. The regression is done by averaging over all the trees. So every tree gives a number, and that eventually gives you an average number. Does that answer the question?
Yeah, so you're saying, okay, there's a vector that you talked about that comes in with like how many gates, let's say, and what the noisy expectation value is, and then that goes into the first node. How does the first node, does it operate on all of the elements of the vector, on some of them? How does it determine what to do?
I see. Yeah, so the splitting of the tree on, what's the threshold in the splitting, and also, what features to use to split is based on an algorithm that will minimize, for example, I think it was they call the Guinea purity or some other thing that they minimize. So there's there are various metrics that people can use to do the splitting to train the tree.
Okay, thank you. And feel free to clarify if that answers the question. And then I think we have a question from Ron. In many of your graphs, there are ideal values. Is the code to compute these available as open source?
Uh-huh. Yeah, that's a good question. Yes, all of this code is open source. It's listed in a GitHub repo link on our archive paper, so welcome to check it out. Uh, there is ideal curve here because they're a small scale circuit, so they're classically tractable.
Oh, lovely. Awesome. And thank you, Paul, our video producer here, for posting the link in the chat and also on the video screen. So you can go take a look at the paper and let us know if you have any comments. Folks, this is a great time to post any final questions that you may have. And it's been tremendous because we've had a lot of questions today and you've left plenty of time for questions. So really appreciate you doing that. I think otherwise, maybe Haoran, if you want to share any other words with us or take home messages, this would be a great time.
Yeah, so I hope that this seminar really promotes more discussion on applying machine learning to enhance quantum computation. I think that there are many aspects in that front, many work that can be done. Combining machine learning for quantum computation is a promising avenue for future research, I think. So the message is that it could be a powerful tool for quantum machine learning. For quantum computation.
Thank you. Yeah, and I mean, I'm personally very shocked and impressed how well it already works. So this kind of exceeded my own expectations, which is great. So with that, I mean, I see there's a little more discussion in the chat, which is great to see. I know folks are really excited for this work and for your presentation. And for sharing the code. I see Ron is really grateful for that. So thank you, folks, for tuning in and for being so active and chatty today and for all the questions and comments. Thank you, Haoran, and congratulations again for the great internship and work. And I don't say that just as a biased advisor here, but I mean that quite genuinely and objectively. And folks, this talk will stay recorded, so you can go back and rewatch it. Reach out to Haoran, myself, or the team if you have any deep follow-up questions. And otherwise, we will see you next Friday at noon Eastern Time.